Hi everyone, welcome back to Coding Fab. In today's lesson, we're going to explore an exciting computer vision project, vehicle detection. We'll work with drone footage to detect and classify different types of vehicles using YOLOv8, one of the most powerful object detection models. Together, we'll go through loading and preparing the dataset, training the model, and evaluating its performance using metrics like precision, recall, and mean average precision. If you're new to object detection or computer vision, don't worry. I'll explain each step clearly and show you how to get hands-on experience with real data. By the end of this video, you'll have a solid understanding of how vehicle detection works and how you can apply it to your own projects. Alright, let's get started. 1. Understanding the project. This project falls under the computer vision category of supervised learning. The main goal is to detect and classify vehicles, such as cars and trucks, in drone footage. This is not just about recognizing what's in an image, but also about locating each object within the image using bounding boxes. We are using a pre-annotated dataset from YOLOv8, specifically the drone crossroad tracking dataset, which includes labeled images taken from aerial drone footage. These labels specify the class of each vehicle and its location in the image, which means bounding box coordinates. This makes it possible to train an object detection model without needing to label the data manually. However, if you have your own images, you can create your own dataset by annotating each image with bounding boxes and class labels using tools like YOLOv8's built-in annotation interface. It gives you the flexibility to build custom models tailored to your specific use case or environment. The task is a classic example of object detection, where the system must not only identify the class of each object, but also determine its position within each frame. To perform this task, we use YOLOv8, a state-of-the-art object detection algorithm known for its speed and accuracy in real-time detection tasks. YOLOv8 is designed to process images and videos efficiently while maintaining high detection accuracy. To evaluate the model's performance, we use metrics specific to object detection, including mean average precision that measures precision across all classes and thresholds. Precision and recall assess the correctness and completeness of predictions. Intersection over union measures how well predicted bounding boxes match the actual ones. We'll develop and train the model in Google Colab, which is particularly suitable for this kind of computation-heavy task. Colab provides free access to GPUs, which significantly speeds up training and allows even resource-intensive models like YOLOv8 to be trained without the need for a powerful local machine. Key tools include Ultralytics YOLO library for model training and inference, RoboFlow for downloading, organizing, and preparing the dataset. And we'll follow the workflow as shown in the upper right. Okay, let's dive in. 2. Loading data. The goal is to download the annotated dataset to your environment. First, go to YOLOv8 and search for a public dataset called Drone Crossroad Tracking. Once you find it, click to open the project page where you'll see dataset details and class information. Navigate to the Dataset or Versions tab, then click on the Download Dataset button. If the dataset is not directly downloadable, you may first need to click Fork Project to copy it into your own RoboFlow workspace. When downloading, you will be asked to choose the export format. Select YOLOv8 as the target format for this project. After selecting YOLOv8, RoboFlow will generate a custom download script for your chosen dataset. Copy that script and paste it into your coding notebook. In this example, we're using Google Collaboratory, so you can run the script directly in a cell. Once the script runs successfully, you'll see folders like Train, Valid, and Test, each containing images and label subfolders. You will also get a data YAML file, which YOLOv8 uses to understand your dataset structure. Before training, open the data YAML file and make sure the paths listed for Train, Valid, and Test are correct and match the actual folder structure. 3. Install model. The goal is to install the Ultralytics YOLOv8 library, which allows you to train, validate, and run predictions using a simple Python interface. It's perfect for object detection tasks like vehicle detection. First, install Ultralytics. If you're using Google Collaboratory, before installing anything, it's important to switch your runtime to use a GPU. This will significantly speed up training. At the top menu, go to Runtime and change the runtime type. Under Hardware Accelerator, select GPU. Then click Save. Once you've set the runtime to GPU, run this command in a code cell to install Ultralytics. If you're using Jupyter Notebook, you don't need the first exclamation mark. Next, verify the installation. Once installed, import and check the version with this code. You'll see the version of Ultralytics, then import YOLO. Now you can do loading a pre-trained model, training a custom model, and running predictions or evaluations. YOLOv8 comes in different sizes. You can choose based on your device speed and accuracy needs. This time we'll use YOLOv8N to focus on the processing speed rather than the accuracy. Now you're ready to train the models. Training the model. The goal is to train YOLOv8 on your labeled vehicle dataset so it can learn to accurately detect and classify objects like cars and trucks using bounding boxes. Let's run this code. This tells YOLOv8 to train a custom object detection model using the dataset and configuration specified. The data tells YOLO where your dataset is located. The data YAML file includes the paths to your training and validation images, the number of classes, NC2, and the list of class names. So it's the link between your data and YOLOv8. The epoch's 50 inches means the model will train for 50 complete passes over your training dataset. You can increase this number later if the model hasn't fully learned. Image size 640 inches resizes all training images to 640 by 640 pixels. It's a standard size that balances accuracy and training speed. Smaller sizes are faster, larger sizes are more detailed but slower. Batch 16 inches means that the model is trained using 16 images per batch. It affects memory usage, so adjust depending on your GPU. If training crashes or is slow, reduce to 8 or 4. After the training, you'll see a folder called Runs with Best PT and Summary images. The Best PT is your best trained model, so keep this file safe. It's the one you'll use going forward for making predictions and evaluation. Confusion matrix shows class confusion during validation. For example, your model predicted car correctly 939 times. It confused car as background 143 times. This means it missed those vehicles. The results image shows the training and validation metrics. The first 3 in the top row show training losses. Train box loss shows how well bounding boxes are fit, lower is better. Train class loss shows classification error, mislabeling objects. Train DFL loss means distribution focal loss for box precision. All training losses are steadily decreasing, which means learning is progressing well. The first 3 in the bottom row show validation metrics. They are also going down. Good generalization. Precision shows how many predicted boxes were correct. It's improved to around 0.85. Recall shows how many true objects were found, rising to about 0.85. Mean average precision 50 inches means average precision with IOU 0.5, reaches around 0.86. Mean average precision 50 to 95 inches means stricter mean average precision, IOU 0.5 to 0.95 average, peaks at around 0.54. Val batch 0 pred shows a sample visual output of predictions the model made on the first batch of validation images. It gives you a quick glance at how your model is performing, like are the boxes accurate? So helps you visually identify problems early. 5. Validation. The goal is to measure how well your trained model performs on data it has never seen before. This helps you understand how accurate your model is, detect overfitting, good training performance but poor generalization, and decide whether your model is ready for real use or needs more training. Let's load your best trained model and makes predictions on each validation image. Then you'll see these metrics and validation folder under the run folder with result images like the training ones. From the result of the metrics, the model was evaluated on a total of 35 validation images, which included 1,147 vehicle instances across all classes. Overall, the model achieved a precision of 90.3%, meaning most of its predictions were correct. Its recall was 81.9%, indicating it successfully detected the majority of real objects. The mean average precision at IOU 0.5 was 88.9%. IOU 50 to 95 was 55.4%. By the way, what are the mean average precision at IOU 0.5 and 50 to 90? They are often used in computer vision. First, intersection over union. Let's say there is a photo of a cat with two boxes drawn around it. The blue box is called the ground truth. This shows the correct location of the cat as labeled by a human. The red box is the prediction. This is where the computer model thinks the cat is. Where these two boxes overlap is labeled intersection. This is the part that both the ground truth and the prediction agree on. It means the model correctly found this part of the object. Now, IOU, which stands for intersection over union, is a score that tells us how much the predicted box overlaps with the correct one. It is calculated by dividing the area of the overlap by the total area covered by both boxes combined. If the prediction perfectly matches the ground truth, the IOU will be 100%, meaning it's a perfect prediction. If there is no overlap at all, the IOU will be 0, meaning the prediction is completely wrong. In this example, because the red and blue boxes only partially overlap, the IOU would be somewhere between 0 and 1. This helps us measure how well the object detection model is performing. Next, mean average precision. It is a common metric used to evaluate how well an object detection model performs. It tells us how accurately the model detects objects and how well it avoids false detections. To calculate mean average precision, we first calculate something called average precision for each object class, like cat, dog, or car. Average precision measures how well the model performs across different levels of recall and precision. Once we have the average precision for each class, we average them all together. This final score is called mean average precision. A higher map means the model is better at detecting objects correctly. Mainly, two different thresholds of mean average precision are used. Mean average precision 50 is a version of mean average precision where we only count a detection as correct if the IOU is 50% or more. This means that the predicted box needs to overlap with the correct box by at least half to be considered a correct match. This metric is easier to pass, so the score is usually higher. It is often used in many YOLO model benchmarks. Mean average precision 50 to 95 is a more detailed and stricter version of mean average precision. Instead of checking overlap at just one level, like 50%, it calculates the average precision at 10 different IOU thresholds, from 50% to 95% in steps of 5%. Then it averages all these average precision scores. This gives a much more complete picture of how well the model detects objects, not just when it's kind of close, but also when it needs to be very precise. Let's go back to the result. In this case, the mean average precision at IOU 0.5 was 88.9%, which shows the model is performing well in terms of detection accuracy. Under stricter evaluation using mean average precision 50 to 95, the score was 55.4%, still reflecting good performance under tighter box matching requirements. When looking at performance by class, for the car class, which had 1,082 instances, the model achieved 88.2% precision, 82.3% recall, and a mean average precision 50 of 89%, showing that car detection is very reliable. For the truck class, there were only 65 instances, which is a much smaller amount of data. Despite this, the model performed very well with a precision of 92.3%, recall of 81.5%, and a mean average precision 50 of 88.8%. This suggests that even though there were fewer truck examples in the training data, the model learned to detect them effectively, which is a very promising result. 6. Prediction. The goal is to use your trained model to predict bounding boxes and classes for vehicles in new media, images, or videos. This demonstrates the model's real-world application. Let's make predictions on the image in the test folder. YOLO will draw bounding boxes with labels, and the output is saved under the Runs folder. This is one of the images from the prediction. You can show several images using for loop and image and display method like this. The image is a bit hard to see, but it seems like the model detects cars and trucks correctly. Let's do the same thing for the video image. The video image is downloaded from the platform that provides free short videos like Pexels. YOLOv8 processes the video frame by frame. After the process, you can directly show the video in your notebook with this code. If your video output type is AVI, please convert it to MP4 with this code. Looking at the results in the video, it appears that cars and trucks are detected accurately. There seems to be no difference from the validation results. Now that you've successfully trained and validated your YOLOv8 vehicle detection model and tested it on both images and videos. If you'd like to improve performance, consider training the model for more epochs, switching to a larger model like YOLOv8s or YOLOv8m, or balancing your dataset by adding more examples of underrepresented classes like trucks. You can also experiment with better data augmentation using RoboFlow. Next, it's a good idea to test the model on real-world footage, such as dash cam videos, traffic footage, or live webcam streams, to see how well it generalizes outside of the training data. Once you're satisfied with its accuracy, you can export the trained model to formats like ONNX, TensorFlow Lite, or TorchScript, depending on your deployment platform. This makes it possible to integrate the model into mobile apps, web applications, or edge devices like Raspberry Pi. And that's it for today's lesson on this topic. We explored how to detect and classify vehicles in drone footage using YOLOv8. You saw how to prepare the dataset, train the model, and evaluate its performance with metrics like precision, recall, and mean average precision. Working on a project like this helps you see the power of computer vision in real-world scenarios. It's a fantastic way to improve your understanding of object detection, while also building skills that can be applied to surveillance, transportation, and even autonomous driving technologies. Keep practicing, try different datasets, fine-tune your model, and see how much better your results can get with experimentation. Okay, thanks for watching today's lesson on coding Fab. I hope you found these tips useful and feel more confident. Remember, practice makes perfect, so try using these tips in your project. If you enjoyed this video, don't forget to give it a thumbs up, share it with your friends, and subscribe for more Fab coding lessons. Until next time, keep practicing and stay Fab.